Hello, this is Group 5, and we're going to present on predicting life expectancy. I'm Sunny Park.
I'm Mark.
I'm Michael.
This is the table of contents consisting of background and research questions, EDA, analysis, and conclusion. So let me start by explaining what life expectancy is. Life expectancy at birth is the average number of years a newborn is expected to live. When WHO announces life expectancy, they calculate it differently depending on ages and countries. Then also they mainly use age-specific death rates in their calculation, such as the number of surviving to age X and probability of dying between ages X to X plus 1. So looking at world life expectancy, it has shown a steady increase from 1950 to 2025, saying that in 2025 it's going to be 73.5 years. Of course, this is global average, not country specific. So why does predicting life expectancy matter? First, it can help reduce global disparities in life expectancy. The map shows the differences in life expectancy by countries. The paler the color, the shorter life expectancy. And the deeper the color, the longer it is. While Nigeria shows only 54.5 years, Japan has 84.7 years. So based on this, in this project, we aim to identify key factors correlated with life expectancy, which can help us understand these inequalities and offer targeted medical interventions to the countries with lower life expectancy. And also, we can respond more effectively to a future crisis like COVID-19 by controlling the key factors. Second, life expectancy also allows governments to adjust their welfare policies as lifespan extends. This chart shows the countries with the highest elderly population. In 2022, Japan led with 29%, and by 2050, Hong Kong is projected to lead with 40%, followed by South Korea and Japan. Especially in such countries, the extended lifespans without any pension reform may lead to benefit shortfalls, which means some people might not be able to receive pensions. So predicting life expectancy allows governments to adjust their pension systems and retirement age to ensure long-term sustainability of pension systems. So from this, we established following research questions. What model best predicts life expectancy? And what are key health-related factors that affect our life expectancy? And to help answer these questions, our hypothesis would be adult mortality has the strongest correlation with life expectancy, and also development status will also impact life expectancy.
The part covers an overview of the data set as well as the steps taken during the EDA to clean the data. The data set was published in Kaggle by an individual, and its source data comes from Global Health Observatory, WHO, World Health Organization, WHO, and the UN website. In our cleaning stage, numbers of values were replaced using Burbank figures. The time span covers 2000 through 2015, and it contains 2,935 observations and 22 variables. Here's the missing data matrix. It highlights that certain variables contain numerous gaps, and a few records shows a substantial proportion of missing entries. Bar chart indicates that hepatitis B, GDP, and population exhibit substantial missingness. Moving on to the next part, the population columns was removed because over 20% of its entries were missing, and some values contain digit level errors. Additionally, since its correlation with life expectancy seemed to be minimal, it was excluded. Similarly, any row with 4 or more missing variables, over 20% of all fields was removed as insufficient for reliable analysis. Anomaly and outlier detection was proceeded in 2 steps. First, any 0 values in variables that cannot logically be 0, such as infant death, under 5 deaths, and percentage expenditure, were flagged as anomalies. Second, statistical outliers were identified using a t-score larger than 5. Comparing these 2 charts, both charts reveal high incidence of zeros for infant deaths under 5 death, and percentage expenditure. In stage 2, observations with t-scores greater than 5 were identified, and the code on the slide showed its calculation and the results. After detecting anomalies and outliers, the variables are assessed whether the variables should be dropped. Since infant deaths and under 5 deaths and percentage expenditure contain more than 20% of invalid values, it is appropriate to remove these variables from the data set. Despite the high proportion of missing variables, infant death and under 5 deaths will be retained and imputed because we predict that they have a strong correlation with life expectancy. However, imputing with these same variables entails a risk to suffer from high bias. All remaining variables, apart from infant death and under 5 deaths, were imputed using respective means methods. As I have mentioned, that imputing infant death and under 5 deaths entails a risk to suffer from high bias. To mitigate bias, values are imputed using the World Bank annual global averages. We impute each values by matching it to the world average for its corresponding year. Since data contains qualitative data variable and status was developed and developing, applying binary encoding converts qualitative data to numerical form. Visualization revealed high multiple linearity. Therefore, infant death and thinness 5 to 9 years were removed, since under 5 deaths and thinness 1 to 19 years capture equivalent information. For analyzing the data, log transformation using log1p is applied to these variables to stabilize and align scales.
After data cleaning, I will explain how we analyze data. First, let's see the data set. It contains 193 countries, and those features such as education, GDP, BMI, HIV, healthcare spending, mortality, those are most important features. First, let's do the data visualization. We will see which feature, the correlation between features and life expectancy. After that, we can get the coefficient of those features. The higher the coefficient, the higher the correlation between each features. Introduce the next one version.
So we like to use loss regression or regression analysis. So loss analyzes the relevant coefficients and will remove coefficients that are not necessary. We use the grid search TV to find the optimal alpha, which is somewhere around 0.02. And as a result, we remove alcohol and hepatitis B as factors. You can see on the selected features graph that the most important by far feature was actually HIV and AIDS presence, followed by schooling, and then the income composition of resources. You can see also on the coefficients of the function of the regression, the line that we use, and also the graph of the coefficients. So the most positive factors, or the most positive predictors, were schooling, income, and GDP. And the most important negative predictors were adult mortality, fitness from ages 1 to 19, and HIV and AIDS. For our actual regression itself, we had a train and test R-squared ratio of 0.79 and a root mean squared error of around 3.5, although I forgot to include this part. I'd say overall it has good explanatory power. One thing I want to note is that the observed versus predicted graph has a right tail. I think it makes sense if you consider the data, because you will get diminishing returns on healthcare investment as age increases towards the, let's say, the limit of what current technology can allow us to do, which would explain why the observed life expectancy was more right-tailed on the right side. And the variance of residuals, I'd say, is relatively even throughout. I'd say there are probably some minor issues with the data regarding bias at certain ages, and also when we filled in data with the average mean, that may have skewed data in some ways. Finally, for conclusion, I'd say for future work, we probably should have inspected and chosen the data more carefully to reduce data skewing and improve the normality of errors specifically. I'd say there was definitely some issues with data bias and missing information that made the data set a little bit more difficult to work with than most others. The key predictors we found were schooling, income, and HIV and AIDS presence, as opposed to adult mortality. We also aided our variable selection by removing factors like alcohol that I may have thought were important before, but were actually not that important. But I think our next steps would be to try other models like XGBoost and hopefully reduce more outliers to make their data a little more palatable for data analysis.
Thank you very much. So, questions, comments? Any questions, comments on the research?
So I think there was something about the mortality rate between 5 to 9 and 1 to 19 years. And then I think there was the part where correlation between survivability from 1 to 19 years old and 5 to 9 years old. And then because it had high collinearity, you guys removed it. Was my understanding correct?
Yeah, that's correct. The data set that we used, basically infant deaths is already included in under 5 deaths, so we'd be using the same data for 2 variables, which of course would result in multicollinearity. And then 5 to 9 years, of course, I mean, the variable name itself states that 5 to 9 year age range was already included in the 119.
So you just removed the 5 to 9 years and you kept the 1 to 19 years?
Yes.
Any other questions, comments? I'm very much impressed by the high accuracy. Can you share the plot, the predicted versus observed? This is unusually highly accurate, I would say, for a real data set. Have you checked the results for the top rankers in the kind of competition. So how your results compare with the results?
Actually, I'd say this R-squared value was a little lower than some of the other people that we saw, at least on Kaggle. Some people were utilizing decision trees, I believe, and at least for our linear regression, I'd say 0.79 was around the average. I actually tried this with polynomial regression and got like 0.866, which was even higher, but I thought that it may have been overfitting. Overall, I mean, I've seen people get like 0.9, so I think that like there's very, very high R-squared values overall, but we wanted to avoid overfitting as much as possible, so we opted to use lasso instead.
So the accuracy is so high, it probably indicates overfitting, may limit its use in real application, but as a first step, is actually, I think, very useful model. Can anyone explain a little bit about how you imputed the missing values?
So for the columns except for infant death and unreplied death, I used the main imputation method. And for infant death and unreplied death, we use the value external data from row bound and impute these value by matching it to the row average, which is corresponding.
Okay, thank you. Maybe one more question or comment? If not, let's thank all the speakers. Thank you very much.